This is section 3.7, rates of change in the natural and social sciences. So the homework is 7 through 19 odd. This is not a very long section. So there's really no formulas except to know that the first derivative is velocity, second derivative is acceleration if we're given a distance function. Okay. And let's see, we just have 7 through 19. So let me go ahead and show that to you right now. There's 7. I think you can see 9 there. 11. 13. 15. 17. And 19. Okay. All right, number 7. Total height is 2 plus 24.5 t minus 4.9 t squared. So that's a height function. The velocity is the first derivative, so h prime is 24.5 minus 9.8 t. The velocity at 2 seconds, just plug in 2, 24.5 minus 9.8 times 2, 4.9 meters per second in this case. The velocity after 4 seconds, plug in 4, 24.5 minus 9.8 times 4, negative 14.7 meters per second. Positive means the particle is going up, negative means the particle is going down. Part B, particles at rest reaches the highest point also, just temporarily. So I set the velocity equal to 0. So 24.5 minus 9.8 t is 0. Solve for t, 24.5 divided by 9.8, 2.5 seconds. Okay, and C, what's the height at 2.5 seconds, which is the maximum height. So maximum height, I plug in 2.5 to the original. 2 plus 24.5, 2.5, minus 4.9, 2.5 squared, punch it in the machine, 32.625 meters. D, you want the height equal to 0, okay, when it touches the ground. So I set 0 equal to negative 4.9 t squared plus 24.5 t plus 2. I would multiply both sides by negative 1 to make it nicer. 4.9 t squared minus 24.5 t minus 2, and etc. Plug in the quadratic formula. Problem 11. Okay, so you're given the wafer is 15 millimeters each side, in general x. Okay, and we're talking about the effect of changing x. So area is x squared, dA dx is 2x using the Leibniz notation. Okay, a prime of 15, 2 times 15 is 30 millimeters squared per millimeter. Okay, you could say it's 30 millimeters, but it actually is more meaningful to say 30 millimeters squared per millimeter, which means at a length of 15 millimeters, a change of length of 1 millimeter would change the area by about 30 millimeters squared. Okay, then it says something about the rate of change is half the perimeter. Well, the perimeter is 4x, half the perimeter is 2x. That is dA dx, as you can see here. Okay, and I want you to illustrate with a picture. So here's x. If I change it by delta x, so delta x, the change in area is this piece, and this tiny piece here. So this is x by delta x. This is x by delta x. This is delta x squared. So delta A is x delta x plus another x delta x plus delta x squared, or 2x delta x plus delta x squared. Divide both sides by delta x. Delta A is 2x plus delta x. So as delta x approaches 0, then we have dA dx approaching 2x plus nothing, or 2x. Okay, 13. So I made a little table. Area is pi r squared with given r. So r of 2, plug in 2, 4 pi, 2.1, 4.41 pi, 2.5, 6.25 pi, 3 gives me 9 pi. Okay, so they ask for the average rate of change from 2 to 3. So average rate of change is really the slope of the line joining the 2 points. So 9 pi minus 4 pi, that's like y2 minus y1, divided by x2 minus x1, 5 pi. Okay, then from 2 to 2.5, a smaller interval, do the same thing. 6.25 pi minus 4 pi divided by 2.5 minus 2, 4.5 pi. 2 to 2.1, so we're making the interval smaller and smaller. So 4.41 pi minus 4 pi divided by 2.1 minus 2, 4.1 pi. Okay, so we're going from 2 to 3, 2 to 2.5, 2 to 2.1. the progression is 5 pi, 4.5 pi, 4.1 pi. So it looks like the instantaneous rate of change is approaching 4 pi. Okay, and we can actually show that that's the case. Okay, area is pi r squared. The derivative a prime is 2 pi r. Plug in 2 pi times 2 is indeed 4 pi. So we seem to be approaching 4 pi. Okay, and it says show that the rate of change is equal to the circumference of the circle. So the formula was pi r squared. The derivative is 2 pi r, which is the formula for the circumference of the circle. Okay, so interestingly, if you take the formula for the area, the derivative is the formula for the circumference. Okay, and this actually shows you that it's reasonable. So here's r. If I increase the radius by delta r, here's r plus delta r. Here's the change in area, delta a. Okay, imagine you snip this and open it up. Okay, then you have something that's almost a rectangle. Okay, it's not quite a rectangle because the inside circle and the outside circle are not quite the same length. But if delta r is very small, i.e. delta r approaches 0, the approximation gets better and better and better. Okay, so we would say this is 2 pi r, this is a delta r. So the change in area, delta a, is approximately 2 pi r times delta r. Divide both sides by delta r. Delta a over delta r is approximately 2 pi r. And the approximation gets better and better as delta r approaches 0, then the inner circle and the outer circle converge to being the same. So dA dr is indeed 2 pi r, which is very reasonable. Okay. Problem 15, surface area is 4 pi r squared. ds dr, rate of change of surface area is 8 pi r. So they ask you to plug in 1, 2, and 3. So plug in 1, 8 pi times 1 square feet per foot. Plug in 2, 16 pi square feet per foot. R equals 3, 24 pi square feet per foot. So they ask you to make a statement about it. Well, as r increases, ds dr also increases. Okay, so as the radius increases, the rate of change of the surface area also increases as the ball gets bigger and bigger and bigger. Okay, 19, Q of t. Q is a current, t cubed minus 2t squared plus 6t plus 2. Okay, so current, rate of change of charge with respect to time, q prime, 3t squared minus 4t plus 6. That happens to be a parabola which opens up, okay, which means I can find a minimum at the vertex. Okay, then they asked me to plug in t equals 0.5 and t equals 1. So just plug in 0.5 and t equals 1. Lowest current, okay, lowest current, well, right here, looks like the derivative is 0. So take the second derivative, q double prime, that's what, 6t minus 4, set it equal to 0 and solve for t. So that's really all you have to do for that one. And that will give you the time for the lowest current. If they ask for the lowest current, then you just plug in that time into the original. Right, so that was pretty much it for section 3.7.